Hi everyone. So in this video, we're going to be talking about how to find the volumes of solids that are a little bit different from the ones that we've been looking at in the last few videos. So in the last few videos, we've been focusing on solids of revolution, which are solids that you get by taking a region and spinning it around in a circle, either around the X or Y axis or around another horizontal or vertical line. And so the nice thing about volumes of revolution is that they have circular cross sections. And so in this video, we're going to be focusing on shapes that actually don't have circular cross sections. And so we're going to want to go back to this idea that we talked about in the very first volumes video and see how we can basically use that kind of more general formula to find the volumes of other types of shapes. So I just want to quickly remind you of what that kind of other formula was. So remember that the volume of a solid, and I'm going to say it's a solid that is basically lying between x is equal to a and x is equal to b. So kind of like in this picture, right? We see it's probably a little hard for you to see because this is very tiny and I made it bigger so it's a little blurry, but this says A and this says B. So if you have a solid that lies between A and B, and x is equal to B, with a cross section that has an area of A of x, or let me say it this way, such that the area of a cross section at x is given by a of x. So if you have a shape like this where if you were to slice this in different places, you get different areas, right? Like the shape of this is such that cutting it in different places will give you a different area. So that's why I'm writing the area as a function, right? It's a function because it varies. The area varies as x varies. So if you go to like an x value here, so maybe we call this x, well, then you're going to get an area that's a lot smaller than if you choose x to be here, right? So that's why the area is considered a function of x. So how do you actually calculate this volume? Well, you take an integral. So it's the integral from a to b of a of x dx. So in the last few videos, we've focused on solids of revolution, which happen to have circular cross sections. So in the last few videos, we have focused on solids of revolution, which have circular cross sections. And so because they have circular cross sections, their volumes can be computed in a slightly different way, right? We could either do something like if the cross sections are truly circular with no hole in the middle, then you can do the integral of pi times the integral from a to b of r squared. And where does that come from? Well, it's literally exactly the same formula here, because this formula up here says we're integrating the area of each slice, right? The area of the cross section. And here, well, if you put this pi and this r squared together, that gives you the area of a circle. Or then we have the other case where if you had these cross sections that looked like washers, well, then you can't just do pi r squared. You have to do pi times the big radius squared minus pi times the little radius squared. But both of these are consistent with this formula up here. So you want to think of this as kind of like the most general form of this formula. And these two below are like special cases of that formula above. So in this video, what we're going to be doing is really kind of going back to this formula above and looking at some cases of solids where, because the cross sections are not circles, we can't use these two formulas down here. Instead, we're going to need to figure out, what is the area of each cross section based on the information given, and plug that into this formula instead of figuring out, what's the radius, because there will be no radius because we're not going to be talking about circular cross sections anymore. So let me just kind of try to summarize that before we jump into an example. So basically, let me maybe write down one thing that I just said, which is that these are special cases of what we had above, the integral from a to b of a of x dx. And so in this video, we will be looking at, or I'll say it this way, we will be using the formula, the integral from a to b of a of x dx with solids whose cross sections, let me say it this way. It feels a little funny to say whose when you're talking about a geometric shape, not a person, with solids with cross sections that are not circles. Okay, so let's get into an example. And we're only going to do 2 examples in this video, and then there will just be 2 on the worksheet, and I think only 2 on the homework. This just isn't as, I'd say, important as volumes of revolution, so we're just not going to spend quite as much time on it, but I think it is really important because it can help you really understand where the volumes of revolution formula comes from, in a sense. Okay, so I'm going to start by describing this shape to you, and then I'm going to pull up something that will help you visualize it, because I think these can actually be even more challenging to visualize than the volumes of revolution. So this says, find the volume of the solid with a base that is a circle of radius 2. So I have the base drawn here. And it says cross sections taken perpendicular to the x-axis. So that means if we cut it like this way. So if you cut it this way, what you'll see is an isosceles right triangle, and I wrote with one leg along the base. And so what I mean by that is that if you take this cross section that we just cut here and you were to kind of pick it up and see what it looks like from the side, it would be an isosceles right triangle. And so what's an isosceles right triangle? It's a triangle where it's a right triangle, and additionally, 2 of the legs have the same length. So this would be the base of that triangle, and then it will also have another side that is perpendicular to it that has the same length, and then it has a hypotenuse. So this shape, no matter where you slice it, if you're slicing it in this direction, if you were to remove that slice and look at it, you would see a right triangle that looked just like this one. So let me pull up a kind of a 3-dimensional thing that will help you hopefully get a better sense of what these look like. So this is, I think, another really cool tool, and I'll link this. So I put in the functions here that are kind of form the boundaries of the base. So I had to put in positive square root of 4 minus x squared to get the top half of the circle, and then negative square root of 4 minus x squared to get the bottom half of the circle. So I guess I should have said that here. The equation for this circle, right, if you were to write the equation of this circle as a whole, the equation would be x squared plus y squared is equal to 4, right? That's the equation of a circle with radius 2. But if you wanted to split it into 2 functions, then the top half would be y is equal to 4 minus, or square root of 4 minus x squared, and then the bottom half would be y is equal to negative square root of 4 minus x squared. Okay, so let's go back to this, this visualizer. So right now what we're looking at is we're looking at this solid from the top. So we see a circle. But I'm going to now kind of tilt it to the side, and we'll see that it's a very funny shape. So it looks like this. So if you look at it like directly dead on from the side, it looks like a right triangle. And the reason for that is because all of the cross sections are right triangles. So what I'm going to do now, like hopefully now you have some kind of sense of what this thing is shaped like. What I'm now going to do is change the filling to become more transparent, because now we're going to look at what the different cross sections look like. So I'm going to take this little part that says move me, and I'm going to slide it, and let me make this even a little bit more transparent. So if I slide this move me, it's showing us what all the different cross sections look like. So notice that when you're at the very end of the circle, because the base is so small, the height is also small, right? Because it's an isosceles right triangle. So the base and the height are the same. But then as I slide it along further and further along the circle, well, now we're getting to parts of the circle that are wider. And so this triangle is also getting taller. And then you hit the middle, and that's kind of the tallest it gets. But then as you slide it more this way, it gets smaller and smaller and smaller. So basically, because this is an isosceles right triangle, the base of the triangle also dictates the height of the triangle. And so that really is what gives this shape where it kind of curves upward and then back downward. So that's what we want to be visualizing. And this is the shape that we're trying to find the volume of. So what do we have to do here? Well, we basically are going to be using just the that integral formula that we wrote down earlier. So we're going to be doing some kind of a variation of the integral from a to b of a of x dx. So our job is to figure out what is the area of a cross section. So this is going to be the area of a cross section if that cross section is taken at x, at an x value of x. So like in the picture we have here, this x value where I drew this, this vertical line, that would be x. And so we need to figure out what would be the area of the right triangle that would be at that piece, at that part of the solid. So again, looking at this right triangle I drew, this gives us an idea. So I drew this blue line to remind you that that's the same as what we see here. And then it also, again, has another side that's the same length as the base because it's an isosceles right triangle, and then it has the hypotenuse. So how do you find the area of an isosceles triangle, or any triangle for that matter? Well, you do base times height over 2. Right? So area of a triangle is going to be equal to base times height over 2. And so basically what we need to figure out is, looking at where we've drawn this and kind of using the information from the function, we need to figure out what the base is and what the height is. So let's start with the base, and then we'll see that actually the height will come along very easily. So how would you find the base? Well, how would you find the length of this blue line? Well, one guess you might have is just to use this function, right? So y is equal to square root of 4 minus x squared. And that's part of the answer, right? So if you were to plug any x value into this function, that wouldn't give you the entire height. What that would actually give you is this distance, right? So this would give you, so this distance here would be the square root of 4 minus x squared, where if you plug in any x value into that function, it will tell you what that distance is. And so that would be true whether we drew the cross section there, whether we drew it here, 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 no matter where we draw it, if you just plug in whatever x value you're at into square root of 4 minus x squared, then you'll get that distance in green. But that's not the whole distance, right? That's half of it. And so really what we want for our base is we want to do 2 times, let me use green to coordinate here, 2 times the square root of 4 minus x squared, right? Because the distance of this entire blue line isn't just one copy of 4 minus x, or square root of 4 minus x squared, it's 2 times it. So that's our base. And so what is the height of this triangle? Well, we know that it's an isosceles right triangle, so we actually know that the height is the same as the base, right? So the height is the same as the base. And so that means that the height is also equal to 2 times the square root of 4 minus x squared. And so now we can go and plug that into our area formula for the triangle. So in this specific case, our area is going to be 2 times the square root of 4 minus x squared times another 2 times the square root of 4 minus x squared, all divided by 2. And so if we multiply this out, we're going to get 4 times 4 minus x squared, right? Because the square roots cancel each other out. And we divide that by 2. And then that simplifies to 2 times 4 minus x squared. And we could distribute that and get 8 minus 2x squared. So that is the area of the triangle. So that is the area of our cross section. And that's exactly what we were looking for, right? So whatever we find for our area here, that is exactly what we want to put in here. So A of x is the area of our cross section. And so now all we have to do is figure out what the bounds are, and then we can just go ahead and integrate. So what are the bounds in this case? Well, we look at basically where is our object positioned? What is the smallest and largest x value that is going to be part of a cross section? And so the first one would be -2. And the last one would be +2. That's the first and last place where it makes sense to actually take a cross section. So putting this all together, we can now say that the volume, let me go back to black to contrast this a little bit. So the volume is going to be the integral from -2 to 2 of our area function. So our area function was 8 minus 2x squared dx. And now we can just integrate this. And actually, you could make this a little easier for yourself by observing that 8 minus 2x squared is an even function. And so anytime you have an even function, you can, instead of going from a negative number to a positive of the same number, you can just say it's 2 times the integral from 0 to the top number. That's kind of a nice trick. And the reason that's a useful trick is that as we've seen, plugging 0 into these functions is generally very easy. So you might as well set yourself up to do that. Okay, so what do we get as our antiderivative? Well, we have 8x, and then we have 2/3 x cubed. And then we are plugging in 2 and we're plugging in 0. So altogether, this is going to give us 16x, or actually let me not do that. Let me leave the 2 on the outside and evaluate first. So when we plug in 2, we get 16, and then we get 2/3 times 8, and that's it, because we don't have to plug in anything with 0. And so this gives us 32 minus, so now we have 4 times 8, so that's 32 over 3. And so this gives us now, if we make a common denominator, we would have 96 over 3 minus 32 over 3. And that gives us a total of 64 over 3. So you might have noticed, or you might think it's weird, like, well, why is there no pi? Why didn't we square anything? It's because we're not dealing with circular cross sections. So the only reason that there's a pi in this formula is because it's a special case of this formula, and it's a special case where the cross section is a circle. So if the cross section isn't a circle, there's no reason to put a pi there, right? So really all we're doing is we're going back to this kind of general formula, and we're just figuring out what is the area of each cross section in this specific case. And so because these cross sections were triangles, that's why we drew a triangle and we found the area of a triangle. So basically the area function that you'll get is going to depend both on what kind of shape you have as your cross section, but also it will depend on your function, right? So we started by saying, okay, we have a triangle and that's the area formula we're going to use. But then in order to actually figure out what the base and the height were, that relied on us, looking at our specific function. Okay, so let's look at another example. And again, we'll do something to actually visualize this in a moment. So in this case, we have a solid that has a base that's a right triangle with a base and height of 9. So I know I'm using the word base here twice. So the first time I say base, I mean it's the base of the solid. And the second time I say base, I mean talking about the base of the base. So right, in this case, the base is triangular, so we can talk about the base of the triangle. So the base of the solid is a triangle, a right triangle with base and height of 9. So I went ahead and graphed that, right? So notice that it didn't give you any equations, but you can choose to draw that triangle on the XY coordinate plane and position it with the corner at the origin, and then that will make it really easy to come up with the equation of the line. So in this case, what equation would this line be? Well, it would be y is equal to 9 minus x, or negative x plus 9, right? It has a slope of -1 and a y-intercept of 9. So what else we need to know here? Well, the cross sections in this case, so we're still taking them perpendicular to the x-axis, so we're taking cross sections like this. In this case, the cross sections are actually squares. And so what that means is that if we were to take this slice that we made here and take it out, we would see that we would have the same base, but then it would actually just be a square. So all of these 4 sides are going to have the same length. So let's take a peek at what this shape actually looks like. So that one's here. So again, looking at it from this view, we see that it just looks like a triangle, right? Oops, sorry, it got a little glitchy. Let me try to return this. Yes, there we go. So that is just looking straight down at it, right? That's the base. But as soon as I turn this, I can see, okay, this actually isn't just a triangle. There's kind of something more going on here. So let me kind of bring it over this way, and you can see that if you look at it from this side, it actually kind of looks like a square, right? And that's because every time you slice it, like along this way, you get squares as your cross sections. And so when you turn it this way, it kind of just like has a slightly square shape to it. So like I did before, let me make this a little more transparent, and then I'm going to slide this along so you can see all the cross sections. So notice that these cross sections are all squares. And so because the way this base is shaped, they start with being the very biggest possible square, and then the further you go to the right, they get smaller and smaller. Because the base is getting smaller and smaller, and because it's a square, that also forces the height to get smaller and smaller. So all the way to having like the tiniest possible square down there. So yeah, I'll link these, and there's other shapes if you kind of scroll through here. Like, so we did the one that was an isosceles right triangle at the base, and then here's the cross section, and then there's some other possible, you could also have a shape that has equilateral triangles as the cross sections, or semicircles as the cross sections, or really any shape you want. So there's some other ones if you want to peek around here that have other types of cross sections. Okay, so let's get back to this question. So again, what's our goal? We want to do the integral from a to b of the area of the cross section dx. And so we need to figure out, in this case, what is that area going to be? So in this case, we have a square, right? So what's the area of a square? Well, it's, a rectangle would be base times height, but for a square, the base and the height are the same. So you could just say, sometimes I like to just say S for like side. So I would just say it's S squared, right? It's whatever the one side is, all the sides are the same, and so you're just doing one side times another. And so in this case, what is the length of the side? Well, we can go and look at our function and use that to figure it out. So this one's a little simpler than the other one, because if you were just to go to any x value you want, so we could even go to one where you can actually tell. So let's say you're at x is equal to 6. How would you figure out what the length of that blue line is? Well, you would just plug 6 into this function, right? So if you plug in 6, you get 9 minus 6 is 3. And notice that that's exactly the length of this blue line. Or if you plug in 7, you get 9 minus 7 is 2. And that's exactly what the length of this blue line is. So you truly are just looking for something that when you plug in a specific x value, it tells you exactly what the length of that blue line is. And so the general formula for doing that is just 9 minus x. So that is our that's our S, right? Like that's what we said this length was. So this length has to be 9 minus x. And that means that this side is also 9 minus x, right? Because it's a square. And so the area is going to be 9 minus x squared. And then we can multiply that out. And so we would get 81 minus 18x plus x squared. And so that is our area. And so that's exactly what we're going to put into our integrand. And then the last thing is just seeing what the bounds are. So again, with the bounds, you're looking at what is the very first x value where it makes sense to do a cross section, and then what's the very last one. And so the first one would be at x is equal to 0, right? And that's where you'd get this really big square with a height and base of 9. And then the very last one would be at x is equal to 9, because that is where you'd get a base and height of 0. So we can put in our bounds as being 0 and 9. So now we can say the volume is equal to the integral from 0 to 9 of 81, let me use my color coding here, so 81 minus 18x plus x squared dx. And so now we can just integrate this. So the antiderivative in this case is 81x minus, so 18 over 2, which is 9, but we can simplify that in the next step. 18 over 2x squared plus x cubed over 3. And then we're evaluating that at 9 and at 0. So that's going to give us, when we first plug in 9, so these are going to be some slightly bigger numbers. So I don't have this one pulled up yet, so I'll do it now. So it's 729 minus, so 18 over 2 is 9. So we're going to have 9 times 81, which is going to actually be the same number. So that's also 729. And then our last piece here is, so 9 cubed, which is actually the same number again. So 9 cubed is 729, and then divided by 3. So this is going to give us, so this is 729 minus 729. It's funny how this happens sometimes. And then we have plus, so 729 over 3 is equal to 243. And so our final answer is 243. And again, notice there's no pi in there, and that's because in this problem, there's like literally no circles at all, right? So the base was triangular, the cross sections were square. So, and in general, with these known cross sections, unless the problem tells you that the cross section is a circle or a semicircle, which, you know, that could happen. But for the most part, when we have circular cross sections, it's because we're doing a solid of revolution. So for these problems, you can expect to see the cross sections to be either squares, rectangles, triangles, something like that. And so you definitely won't see a pi showing up in your answer. All right, so that is it. So definitely check out the worksheet for today. That will do a couple more examples like this. And in the next videos, we'll actually be doing, so we'll have 3 more videos that are about volumes, and they're going to focus on, we're going to go back to talking about volumes of revolution, and we're going to talk about a new method for finding those volumes.